Quantum physics begins in the smallest known corners of nature, where the familiar rules of everyday life become strangely unreliable. A ball rolls, a candle glows, a clock ticks, and the world around you seems solid, smooth, and reassuringly sensible. But beneath that calm surface, atoms and particles follow a deeper set of rules, where energy arrives in tiny packets, light behaves like both a wave and a particle, and matter seems less like little hard objects, and more like a delicate pattern of possibilities. It can sound mysterious at first, almost as if reality has hidden its instruction manual in a drawer labelled, "Please do not open before bedtime." But quantum physics is not magic, and it is not guesswork. It is one of the most carefully tested scientific theories ever created, built from real experiments, precise measurements, and the stubborn refusal of nature to behave the way classical physics expected. Tonight, the aim is to slow it all down, take it gently, and let the strange little pieces begin to make sense. Welcome to the Late Lab. It's lovely to have you here. Before things get wonderfully tiny, where in the world are you watching from tonight? Maybe tucked under a blanket, curled up on the sofa, resting after a long day, or half listening with the lights low and the room finally quiet. Wherever you are, hopefully you're warm, settled, and ready to wander softly into one of the strangest ideas science has ever uncovered. If you enjoy these calm little journeys through science and would like more of them, liking and subscribing really helps this sleepy corner of the internet keep drifting along. And if you're already subscribed, thank you, truly. Your support makes a real difference, even if the particles themselves remain emotionally unavailable. Now, tonight's subject may be small, but it has a habit of becoming very large in the imagination. Quantum physics asks why atoms are stable, why light can arrive in packets, why electrons seem to spread like waves, and why measurement plays such a surprisingly important role in what we observe. It is the science of the tiny, but it quietly supports chemistry, electronics, lasers, medical scanners, and much of the modern world. So, let's ease into it slowly. What is quantum physics? And why does the universe seem to become most mysterious exactly when science looks at it most closely? For most of human history, the physical world seemed to behave in a way that made a certain kind of comforting sense. Stones fell downward, planets moved through the sky, heat flowed from warm things into cooler things, light travelled in waves, matter appeared to be made of solid pieces, even if those pieces were far too small to see. The universe did not always seem simple exactly, but it did seem as if it should be understandable through steady rules, careful observation, and enough patience. By the end of the 19th century, many scientists felt that physics had come remarkably close to describing those rules. Isaac Newton had given the world a powerful way to understand motion and gravity. In Newton's picture, objects moved according to clear causes. If the position, speed, and forces acting on something were known, its future motion could be calculated. A cannonball, a falling apple, and even the moon could all be understood through the same mathematical language. It was an extraordinary achievement, and it made nature feel deeply ordered, as if the universe were a grand clockwork machine, ticking away with elegant indifference. Then James Clerk Maxwell brought electricity, magnetism, and light into a single beautiful framework. Maxwell showed that electric and magnetic fields were not separate curiosities, but connected parts of one electromagnetic theory. Light itself could be understood as an electromagnetic wave travelling through space at a definite speed. This was not a small discovery. It meant that sunlight, radio waves, visible colours, and many other forms of radiation were all part of the same family. The universe was beginning to look less like a messy collection of unrelated effects, and more like a tidy set of principles wearing different hats for special occasions. Classical physics, as this older framework is now called, worked brilliantly across a huge range of experience. It could describe the swing of a pendulum, the orbit of a planet, the pressure of a gas, the flow of heat, and the motion of waves. It gave engineers, astronomers, chemists, and inventors an astonishingly useful toolkit. The basic expectation was that nature should be continuous and predictable. Energy could vary smoothly. Motion could be traced from one instant to the next. Matter could be imagined as little pieces following definite paths. Light could spread as a wave. Everything, at least in principle, seemed knowable. But in the quiet corners of this success, a few small problems refused to go away. They did not look enormous at first. They were not dramatic enough to make the whole building of physics collapse overnight. They were more like tiny cracks in a very polished wall, easy to ignore perhaps, until someone noticed that the cracks were growing in exactly the places where the foundations mattered most. One crack came from blackbody radiation, the problem of how hot objects emit light and heat. Classical physics predicted the wrong pattern of radiation, especially at high frequencies. The prediction was so badly wrong that it later became known as the ultraviolet catastrophe, which sounds like either a physics problem or a very intense nightclub. Another crack came from atomic spectra. When atoms emitted or absorbed light, they did not produce every possible colour in a smooth spread. They produced sharp, specific lines, as though each kind of atom had its own private barcode written in light. The photoelectric effect created another difficulty. When light shone on certain metals, it could knock electrons loose, but only if the light had a high enough frequency. Making low-frequency light brighter did not solve the problem in the way classical wave theory expected. And beneath all of this sat perhaps the most basic puzzle of all. Atoms existed. They were stable. Ordinary matter did not instantly collapse. Classical physics, especially when applied to electrons moving around atomic nuclei, struggled to explain why atoms did not simply radiate away energy and fall apart. These problems mattered because they appeared at the scale of atoms, electrons, photons, and subatomic particles. They were clues that the old rules, however powerful, were not complete. Classical physics had not failed everywhere. It still worked beautifully for falling stones, flowing rivers, orbiting planets, and most of ordinary life. But at the smallest scales, nature was quietly refusing to behave like a miniature version of the everyday world. Quantum physics emerged because experiments forced it to emerge. Scientists did not invent it because they wanted reality to sound mysterious, poetic, or mildly inconvenient. They accepted it because the measurements kept pointing in the same strange direction. Energy did not always behave as a smooth, continuous quantity. Light sometimes behaved as if it arrived in individual packets, later called photons. Matter sometimes showed wave-like behaviour. Outcomes at the quantum scale often had to be described through probability rather than simple certainty. This marked a deep shift in scientific thinking. Classical determinism suggested that, with perfect knowledge, the future of a physical system could be predicted exactly. Quantum theory replaced that older picture with something subtler. It did not abandon precision. In fact, quantum mechanics became one of the most precise and successful theories in all of science. But its precision was often the precision of probabilities, energy levels, wave functions, and measurement outcomes, not the precision of tiny objects following neat classical paths. That is the important distinction. Quantum mechanics is not magic. It is not a loose invitation to say that anything can happen because the universe is feeling whimsical. It is a rigorous scientific framework built from mathematics and tested through experiment again and again. Its predictions support technologies from lasers and semiconductors to medical imaging and atomic clocks. The theory may feel strange, but it is not vague. It is strange in the disciplined way nature is sometimes strange when it has no obligation to match human intuition. So the basics of quantum physics begin with a simple, quietly unsettling question. Why does the ordinary world appear smooth, solid, and stable when its foundations are discrete, restless, and deeply unlike everyday experience? The answer begins in those tiny cracks in classical physics, where light, matter, and energy first revealed that reality was not less understandable than scientists had hoped. It was simply built from rules far stranger and far more precise than anyone had expected. The first major clue that something was wrong with classical physics came not from an exotic particle accelerator or a mysterious signal from deep space, but from something wonderfully ordinary: the glow of a hot object. You have seen this effect before, even if it did not arrive wearing a lab coat. A piece of metal placed in a fire begins to glow dull red. Heat it further, and the glow becomes brighter, shifting through orange, yellow, and eventually toward white. A toaster filament, an old-fashioned light bulb, a blacksmith's iron, even the surface of a star, all give off radiation because of their temperature. Hot matter does not keep its energy politely to itself. It radiates. Physicists call an ideal version of this a blackbody. The name sounds dramatic, but the idea is fairly simple. A blackbody is a perfect absorber and emitter of radiation. It absorbs all incoming light and heat, reflecting none of it, and then emits radiation according to its temperature. No real object is absolutely perfect in this way, but many objects come close enough for the idea to be extremely useful. A small hole in a heated cavity, for example, can behave almost like an ideal blackbody, because light entering the hole bounces around inside and is very unlikely to escape unchanged. Nature, as usual, finds a way to turn a tiny opening into a physics lecture. The question was this: what pattern of radiation should a blackbody emit? In everyday terms, if an object is heated, how much energy should it give off at each colour or each frequency of light? Experiments showed a clear pattern. At a given temperature, the object emitted most strongly around a certain range of frequencies. As the temperature increased, the peak shifted toward higher frequencies, which is why hotter objects change colour. Cooler glowing objects appear redder. Hotter ones become whiter or bluish-white, because they emit more strongly at higher frequencies. Classical physics tried to explain this using the best tools available at the time. The calculations treated radiation inside a cavity as a collection of waves. The trouble was that the mathematics produced a deeply unreasonable result. It predicted that a hot object should emit more and more energy at higher and higher frequencies, without limit. In other words, it suggested that the ultraviolet part of the spectrum and frequencies beyond it should carry an impossible amount of energy. This became known as the ultraviolet catastrophe. It is a brilliant name, partly because it sounds like the sort of disaster that might require both a fire extinguisher and a pair of sunglasses. But the problem was serious. The prediction did not match reality. Hot objects do not pour out infinite high-frequency radiation. The universe, thankfully, does not turn every oven into a small violet apocalypse. The experiments were clear, and classical theory had failed. This failure mattered because it was not a tiny rounding error. It showed that something basic in the classical picture of energy and radiation was missing. If energy could be exchanged in a perfectly smooth, continuous way, the old calculations led to nonsense. So the solution had to come from changing one of the assumptions that had seemed obvious. In 1900, Max Planck found a way through the problem. Planck was studying blackbody radiation and trying to produce a formula that matched the experimental data. His solution worked beautifully, but it required a strange step. He proposed that energy was emitted or absorbed in small discrete packets, rather than in a perfectly continuous flow. The size of each packet depended on the frequency of the radiation. Higher frequency radiation came in larger energy packets. Lower frequency radiation came in smaller ones. This idea was the beginning of quantization. Energy, at least in this context, did not behave like water pouring smoothly from a jug. It behaved more like coins being exchanged one at a time. The coins were incredibly tiny, of course, far beyond anything noticeable in ordinary life, but the principle was revolutionary. Nature seemed to have a smallest style of transaction at the microscopic level. It did not always pay in smooth installments. At the heart of Planck's proposal was Planck's constant. This constant sets the scale of quantum effects. It is extremely small, which is why quantum behavior is usually hidden from everyday experience. For large objects, the tiny graininess associated with Planck's constant becomes completely overwhelmed, and the world appears smooth. A rolling football does not visibly hop through allowed energy packets. A teacup does not behave like an electron, which is probably just as well for the carpet. But at the scale of atoms, light, and particles, Planck's constant becomes essential. It tells physics where the classical picture begins to lose its grip, and where quantum rules must be used instead. It is one of the central constants of modern science, not because it is large, but because it is quietly built into the behaviour of the smallest things. Planck himself did not set out to overthrow reality. He was not trying to make physics strange for the sake of it. In fact, he was cautious about the meaning of his own discovery. At first, the idea of energy packets could be treated almost like a mathematical trick, a clever way to make the formula match the measurements. But the trick worked too well to remain only a trick. It pointed towards something real. Blackbody radiation therefore became one of the first major cracks in classical confidence. The old world had expected energy to vary smoothly, endlessly divisible into smaller and smaller amounts. But the glow of hot matter suggested something different. Energy itself seemed to come in steps. Tiny steps, almost unimaginably small, but steps all the same. And from that soft glow from heated cavities and careful measurements, quantum physics began to emerge, not as a wild guess, and not as a decorative mystery, but as a necessary answer to a stubborn fact. The universe was not quite continuous underneath. Somewhere deep below the calm surface of ordinary light and heat, nature was already counting. The idea that light might behave like a particle sounds, at first, like a step backward. For centuries, light had increasingly looked like a wave. It could spread out, bend, interfere with itself, and pass through openings in ways that made much more sense if it was imagined as a rippling disturbance, rather than a stream of tiny objects. James Clerk Maxwell's electromagnetic theory had made that wave picture even stronger. Light was not merely something that helped eyes do their useful little job of bumping into furniture less often. It was an electromagnetic wave, moving through space with extraordinary speed and obeying elegant mathematical rules. But then came another awkward experimental fact. It was called the photoelectric effect, and it involved shining light onto certain metal surfaces. Under the right conditions, the light could eject electrons from the metal. This was already interesting because it showed that light could transfer energy to matter. But the real puzzle lay in the conditions required. The electrons were not ejected simply because the light was bright. They were ejected only when the light had a high enough frequency. Frequency means how rapidly a wave repeats. In visible light, lower frequency light appears toward the red end of the spectrum, while higher frequency light appears toward the blue and violet end. Beyond violet sits ultraviolet light, which has even higher frequency. According to the classical wave picture, the energy of light should depend mainly on the intensity of the wave. Brighter light should carry more energy. So, if light were only a smooth wave, then very bright red light should eventually provide enough energy to knock electrons free from a metal surface. It might take a little time, perhaps, but enough brightness should do the job. That is not what happened. Low-frequency light failed to eject electrons, even when it was made brighter. Meanwhile, high-frequency light could eject electrons even when it was quite dim. The result seemed upside down from the classical point of view. It was as though the metal cared less about how much light was arriving overall, and more about the energy carried by each individual portion of light. This was deeply strange. Imagine trying to knock a ball from a shelf by throwing soft snowflakes at it. You might throw more and more snowflakes, but if each one is too gentle, the ball stays where it is. Now imagine one small pebble arriving with enough force to do the job at once. The number of things arriving matters, but only after each one has enough individual energy. The photoelectric effect seemed to suggest that light behaved in a somewhat similar way. Not exactly like pebbles, of course, because nature rarely files its metaphors properly, but close enough to make the point. In 1905, Albert Einstein proposed a bold explanation. Building directly on Max Planck's quantum idea, Einstein suggested that light itself could behave as if it came in individual packets of energy. These packets were later called photons. In this view, light was not only a continuous electromagnetic wave. When it interacted with matter, it could transfer energy in discrete amounts. Each photon carried an energy determined by the light's frequency. This was the crucial step. The energy of a photon depends on frequency, not on brightness alone. Higher frequency light is made of higher energy photons. Lower frequency light is made of lower energy photons. Brightness in this picture is more closely related to how many photons are arriving. A bright red beam may deliver many photons, but if each photon does not have enough energy to free an electron from the metal, no electron is ejected. A dim ultraviolet beam may deliver fewer photons, but each photon can carry enough energy to release an electron. The metal surface has what is called a work function. This is the minimum energy needed to remove an electron from the material. If a photon does not meet that threshold, the electron stays bound. If the photon does meet it, the electron can escape. Any extra energy becomes kinetic energy, meaning energy of motion, carried away by the ejected electron. This explained why increasing the frequency of light could make the emitted electrons move faster, while increasing the brightness mainly increased the number of electrons ejected, as long as the frequency was already high enough. Einstein's explanation was not immediately welcomed by everyone. Light had looked so convincingly wave-like that treating it as particle-like felt almost rude, as if light had turned up to a formal dinner wearing two outfits at once. Yet the experimental evidence kept supporting the idea. Light could still show wave behavior in interference and diffraction, but in the photoelectric effect it behaved as though energy arrived in individual packets. This became one of the strongest early confirmations that quantization was not only a mathematical trick used to explain heated objects. Planck had shown that energy exchange in blackbody radiation could be described in discrete steps. Einstein pushed the idea further and treated those steps as a real feature of light itself. The quantum was no longer hiding inside a formula for glowing matter. It was travelling across the room as light. Einstein later received the Nobel Prize in Physics partly for explaining the photoelectric effect. This surprises many people because he is more famously associated with relativity. But the photoelectric effect was central to the birth of quantum theory. It showed that light, one of the most familiar things in the universe, could not be understood completely through the old classical wave picture. The deeper lesson was calm but unsettling. Nature did not always divide energy however smoothly human imagination preferred. At small scales, light could arrive as photons, each carrying a precise amount of energy linked to frequency. A beam of light was not merely a smooth wash spreading through space. It was also, in the right circumstances, a stream of quantum packets, and with that the crack in classical physics widened. The glow of hot objects had already suggested that energy came in steps. The photoelectric effect now showed that light itself carried those steps into matter. The universe was beginning to reveal a pattern. Beneath the smoothness of ordinary experience, energy was not always flowing like water. Sometimes it arrived one quantum at a time. The particle nature of light solved one problem, but it also sharpened another. If light and energy came in discrete packets, then perhaps matter itself was not as smooth and straightforward as classical physics had assumed. And nowhere was that more obvious than inside the atom. Atoms were already known to be the tiny building blocks of ordinary matter. Every breath, stone, drop of water, grain of dust, and extremely patient biscuit crumb is made from atoms. They're far too small to see directly with ordinary eyes, yet their existence explained chemistry, gases, heat, and the behavior of materials. By the early 20th century, scientists knew atoms were real, but they did not yet fully understand their internal structure. The atom was not simply a tiny hard ball. Something more complicated was hiding inside. For classical physics, this became a serious difficulty. Ordinary matter is stable. Tables remain tables. Air does not collapse into a flash of radiation. The atoms in a cup of tea do not suddenly surrender to mathematical despair and become something else entirely, which is helpful, especially if the tea has just been made. Yet classical electromagnetism seemed to predict that atoms should not survive in the way they clearly do. The key problem involved electrons. Electrons are negatively charged particles, and atoms also contain positive charge. Opposite charges attract, so a negatively charged electron should be drawn toward positive charge inside the atom. If electrons moved around that positive charge, classical electromagnetism said they should radiate energy. A charged particle changing direction, or accelerating, should give off electromagnetic radiation. As it lost energy, the electron should spiral inward. The atom should collapse almost instantly. But atoms do not collapse. They remain stable long enough to build planets, oceans, bodies, bones, bookshelves, and the occasional spoon that somehow vanishes into the kitchen drawer dimension. Something in the classical picture was missing. A major clue came from Ernest Rutherford at the University of Manchester. In the famous gold foil experiment, alpha particles were fired at a thin sheet of gold. Alpha particles are positively charged particles emitted by certain radioactive materials. At the time, one common picture of the atom imagined positive charge spread out through the atom, with electrons embedded inside it, rather like small ingredients suspended in a soft pudding. This was sometimes called the plum pudding model, which is one of the few moments in atomic physics that sounds as if it belongs near custard. If positive charge was spread out diffusely, most alpha particles should pass through the gold foil with only small deflections. Many did, but a tiny fraction bounced back at large angles, as if they had struck something very small, very dense, and strongly positive. Rutherford later described the surprise by comparing it to firing a shell at tissue paper and having it come back. The result revealed that the atom was mostly empty space, with nearly all of its positive charge and mass concentrated in a tiny central nucleus. The nucleus was incredibly small compared with the atom as a whole. If the atom were enlarged to the size of a cathedral, the nucleus might be more like a tiny speck near the centre, while the electrons occupied the surrounding volume. This was a beautiful discovery, but it created an even sharper puzzle. Rutherford's nuclear model showed that atoms had a central positive nucleus, with electrons somehow arranged around it. But if electrons orbited the nucleus like tiny planets around a star, classical physics predicted disaster. Unlike planets, electrons are charged. Charged particles moving in curved paths should radiate energy, so once again, the atom should collapse. The new model explained the scattering experiment, but it did not explain stability. In 1913, Niels Bohr proposed a bold solution, using the emerging idea of quantization. Bohr focused especially on the hydrogen atom, the simplest atom, containing one electron associated with one proton. He suggested that electrons could occupy only certain allowed energy levels around the nucleus. They were not free to spiral smoothly through every possible orbit. Instead, only specific states were permitted. In Bohr's model, an electron in one of these allowed states did not radiate energy continuously. It could remain stable, but it could jump from one allowed energy level to another. If it moved to a lower energy level, the atom emitted a photon. If it moved to a higher energy level, the atom absorbed energy, often from a photon. The energy of the photon matched the difference between the two levels. Light and atoms were now linked through exact quantum steps. This helped explain one of the great mysteries of atomic spectra. When hydrogen gas emits light, it does not produce every possible colour in a smooth rainbow. It produces specific lines. These lines appear because the electron in hydrogen can only move between certain allowed energy levels. Each jump releases or absorbs a photon with a particular energy, and that energy corresponds to a particular colour of light. Bohr's model was not the final version of the atom. Later quantum mechanics replaced its neat electron orbits with wave functions and orbitals, which describe probabilities rather than tiny planets circling a nucleus. But Bohr's model was a vital bridge. It showed that quantization was not just a feature of heated objects or light beams. It belonged inside matter itself. The atom had forced physics into a deeper realization. Stability, light, and structure all seemed to depend on discrete energy changes. Electrons did not simply slide through every possible state. Atoms did not glow in every possible color. Photons carried energy away in exact amounts. The world looked continuous from a distance, but inside the atom, nature was using steps. And that changed the meaning of matter. The solidity of ordinary things was not the result of tiny classical particles calmly obeying familiar rules. It depended on quantum rules that prevented collapse, shaped atomic structure, and allowed light to reveal the hidden order inside atoms. The universe was still stable. But now, for the first time, physicists were beginning to understand that its stability came from something far stranger than clockwork. The stability of atoms was already strange enough, but atoms had another habit that made them even more revealing. They did not simply exist quietly. Under the right conditions, they gave off light, and the light they produced was not random. It came in precise patterns, like a hidden signature written across the spectrum. When an atom emits or absorbs light, it does not usually do so in a smooth, continuous spread of every possible color. Instead, it produces a distinctive set of lines at particular wavelengths. These patterns are called atomic spectra. Each element has its own recognizable spectral fingerprint, because each kind of atom has its own arrangement of energy levels. Hydrogen has one pattern, helium has another, sodium has another. Iron, calcium, oxygen, neon, and all the rest each leave their own marks in light. This was one of the great clues that matter was organized by rules deeper than classical physics had imagined. If atoms could absorb and emit any amount of energy, then their light should have formed a smooth rainbow. Every color should have been possible, but that was not what experiments showed. Instead, when light from a glowing gas was passed through a prism or a spectroscope, the result was often a set of sharp, bright lines against a dark background. When cooler gas absorbed light, it could leave dark lines in an otherwise continuous spectrum. The atom seemed to be speaking, but only in certain notes. Hydrogen became especially important because it is the simplest atom, and its spectral pattern could be studied in detail. A hydrogen atom contains one electron associated with one proton, so it offered the cleanest possible testing ground for early quantum ideas. When hydrogen gas was excited, it emitted light at very specific wavelengths. These lines were not placed at random. They followed a pattern that could be described mathematically, even before anyone fully understood why. In the 1880s, the Swiss mathematician Johann Balmer found a formula that organized some of the visible hydrogen lines. This became known as the Balmer series. Balmer did not discover the deeper quantum structure of the atom, but he helped reveal that the hydrogen spectrum contained order. The lines behaved as though nature were following a numerical rule. That was a powerful clue. It suggested that the atom was not a tiny chaotic object splashing light in every direction, but a structured system with allowed behaviors. Later, Niels Bohr's model of the hydrogen atom gave this pattern a physical explanation. Bohr proposed that the electron in hydrogen could occupy only certain allowed energy levels. It could not sit at just any energy it pleased, like a restless guest choosing any seat at a dinner party. Only certain seats were available. When the electron moved from a higher energy level to a lower one, the atom emitted a photon. The energy of that photon matched the difference between the two levels. Because only certain energy differences were allowed, only certain photon energies could be emitted. And because photon energy is linked to frequency and wavelength, only certain colors appeared. This connected the bright lines of hydrogen directly to electron transitions. A spectral line was not just a stripe on a screen, it was evidence of an electron changing energy inside an atom. Each line represented a specific quantum jump. Not a jump through ordinary space like a tiny flea with academic ambitions, but a change from one allowed energy state to another. The atom lost a precise amount of energy, and that energy left as a photon of a precise wavelength. The same logic also explains absorption lines. If light containing many wavelengths passes through a cooler gas, Atoms in the gas can absorb photons that match the exact energy needed to lift electrons to higher allowed levels. The missing wavelengths appear as dark lines in the spectrum, so atoms can both give away and take in very particular colours, depending on their internal structure and the conditions around them. This made atomic spectra one of the most important tools in science. They were not merely a historical curiosity from the early days of quantum theory, they became a way to identify matter across impossible distances. Astronomers can look at the light from stars, galaxies, nebulae and interstellar gas, then read the spectral lines to learn which elements are present. Hydrogen lines reveal hydrogen, helium lines reveal helium, sodium, calcium, oxygen, carbon, iron and many other elements can be recognized by their spectral fingerprints, even when the source is light years away. This is how scientists know what stars are made of without visiting them, which is fortunate, because even the nearest star would make for a deeply inconvenient field trip. Spectroscopy allows researchers to study the composition of the Sun, the atmospheres of distant planets, the gases in nebulae, and the motion of galaxies. The same quantum energy levels that solved a problem inside the atom also opened a way to read the universe. And this is why atomic spectra mattered so much to the foundations of quantum physics. Quantist energy levels did more than explain why atoms did not collapse. They explained why atoms emit and absorb light in precise patterns. They showed that the structure of matter and the behaviour of light were tied together through discrete energy changes. The atom was not silent. It carried an internal order, and when conditions were right, that order became visible as colour. So the lesson became clearer. Matter did not shine in every possible way. It shone according to the allowed steps hidden inside it. The world may appear smooth from the outside, but at the atomic scale, nature keeps a careful record of what is permitted. And across laboratories, stars, galaxies, and glowing clouds of gas, atoms continue to reveal themselves through those quiet, precise lines of light. By now, light had already begun to behave suspiciously. It had entered physics as a wave, spread itself through Maxwell's electromagnetic theory, and then, in the photoelectric effect, revealed that it could also arrive as photons, like tiny packets of energy. That was strange enough. But quantum physics was not finished rearranging the furniture. The next surprise was that matter itself, the supposedly solid stuff of electrons and atoms, could also behave like a wave. This idea is called wave-particle duality. It means that quantum objects can show both particle-like and wave-like behaviour, depending on the situation and the way they are measured. A photon can arrive at a detector as a single event, like a particle, but it can also produce interference, like a wave. An electron can be detected at a particular place, as if it were a tiny object, yet under the right conditions it can spread, diffract, and interfere in ways that no ordinary little pellet should. At first, this sounds like nature is refusing to choose a lane. But the point is not that electrons are secretly tiny balls one minute and tiny ripples the next, changing costumes in the wings. The deeper lesson is that classical categories do not fit perfectly at the quantum scale. The words particle and wave come from everyday experience. A grain of sand is particle-like. A ripple on a pond is wave-like. Quantum objects do not fully belong to either picture. They show features of both, while being exactly neither in the ordinary sense. The person who pushed this idea into a new form was Louis de Broglie. In the early 1920s, de Broglie asked a bold question. If light, which had long been understood as a wave, could also behave like a particle, then might matter, long understood as particle-like, also behave like a wave? It was a beautifully symmetrical thought, the sort of idea that seems simple once stated, but only because someone else had the nerve to state it first. De Broglie proposed that particles of matter have an associated wavelength. This became known as the de Broglie wavelength. For an electron, this wavelength can be large enough on the atomic scale to matter physically. For larger objects, the wavelength becomes fantastically tiny. But for electrons and other small particles, it suggested that matter should show wave-like effects under suitable conditions. This was not just a poetic idea. It made testable predictions. If electrons really had wave-like properties, then they should be able to diffract. Diffraction is what happens when waves spread and bend after passing through openings or around obstacles. Light waves do it. Water waves do it. Sound waves do it. If electrons could do something similar, then matter itself would have revealed wave behavior. That evidence arrived in the Davison-Germer experiment at Bell Labs. Clinton Davison and Lester Germer studied electrons scattering from a crystal of nickel. A crystal is not just a solid lump. Its atoms are arranged in a regular repeating pattern, rather like a three-dimensional grid. They're rather less useful for hanging kitchen utensils. When electrons were directed at the crystal, they scattered in a pattern that matched what would be expected from wave diffraction. The electrons were not simply bouncing like tiny classical beads. Their behavior depended on wavelength and interference. This was a major confirmation of de Broglie's proposal. Electrons could produce diffraction patterns. Matter waves were real enough to measure. Around the same period, George Paget Thomson also showed electron diffraction using thin metal films. This was especially charming in the history of physics because his father, J.J. Thomson, had helped identify the electron as a particle, while George Thomson helped demonstrate its wave-like nature. The electron, politely confusing two generations of one family, had made its point, but it's important to be careful with the phrase matter wave. An electron wave is not an ordinary wave like a ripple travelling across water. It is not a sound wave moving through air. It is not made of some little material substance sloshing around in space. In quantum mechanics, the wave-like description is mathematical. It is connected to the probabilities of different measurement outcomes. It tells physics where an electron may be detected, how likely certain results are, and how those possibilities can interfere with one another. This is why quantum waves can feel difficult at first. A water wave is easy to picture because the water is physically moving up and down. A sound wave is a pattern of pressure moving through air. But an electron's wave-like behavior is not a wobbling string or a visible ripple. It is a structure of probability, a way of describing possible outcomes before a measurement gives one definite result. The wave is not just in the mind of the scientist, but it is also not a classical wave made of familiar stuff. It sits in that deeply quantum middle ground where the mathematics is precise, but the mental image has to be handled gently. The reason this wave behavior is not obvious in everyday objects comes from scale. De Broglie's wavelength depends on momentum. Tiny particles such as electrons can have wavelengths comparable to atomic distances. But a football, a chair, a spoon, or a sleeping cat has a de Broglie wavelength so unimaginably small that its wave behavior is completely unnoticeable in ordinary life. Technically, quantum theory still applies. Practically, the wavelength is so tiny that the object behaves classically. A tennis ball does not diffract around the net, which is probably for the best, as the rules of sport are already complicated enough. So the strangeness now ran both ways. Light, once treated as a wave, could behave like a particle through photons. Matter, once treated as particles, could behave like a wave through de Broglie wavelengths and electron diffraction. The old categories had not been destroyed, but they had been softened. At the quantum scale, nature was not made of tiny versions of everyday objects. It was made from entities whose behavior depended on deeper rules. And with matter waves, quantum physics moved closer to its modern form. Electrons were no longer simply little points circling atomic nuclei. They had wave-like properties that helped explain why atoms have structure, why energy levels exist, and why matter behaves as it does. The universe still looks solid from a distance. But underneath that solidity, electrons were beginning to look less like miniature planets, and more like patterns of possibility, spread through space until the moment nature gave a definite answer. The wave-like behavior of matter is already strange, but there is one experiment that seems to gather much of quantum physics into a single, quiet puzzle. It is called the double-slit experiment. Its basic arrangement sounds almost too simple to be troublesome. A source sends light, or electrons, or another quantum object toward a barrier with two narrow openings. Beyond the barrier sits a screen or detector. The question is only this: where do the particles arrive? For ordinary particles, the expectation is straightforward. Imagine throwing tiny grains of sand at a wall with two vertical gaps. Some grains pass through the left gap, some pass through the right gap. On the screen behind the wall, there should be two main bands matching the two openings. Each grain travels through one slit or the other, lands in one place, and behaves in a nicely sensible way. Sand, to its credit, is rarely philosophically difficult. For waves, the result is different. If water waves pass through two openings, each opening becomes a source of spreading ripples. The ripples overlap. In some places, wave peaks meet wave peaks and strengthen one another. In other places, peaks meet troughs and cancel out. This produces an interference pattern, a series of stronger and weaker regions. Interference is one of the clearest signatures of wave behavior. Long before quantum physics, Thomas Young used a version of the double-slit experiment to study light in the early 19th century. At the time, there was a major debate over whether light was made of particles or waves. Isaac Newton had supported a particle-like view of light, while other scientists developed wave explanations. Young's experiment showed that light passing through two slits could create an interference pattern. That was powerful evidence that light behaved as a wave. A beam of light did not simply form two bright patches behind the two openings. It formed alternating bright and dark bands, the visible mark of waves overlapping. For a while, that seemed to settle things rather comfortably. Light was a wave. Then quantum physics arrived and made itself comfortable in the chair marked unresolved. Einstein's explanation of the photoelectric effect showed that light could also behave as if it came in photons, individual packets of energy. So the double-slit experiment became more mysterious. If light was sent through the slits as individual photons, one at a time, what would happen? The answer is one of the most unsettling results in science. Each photon arrives at the detector as a single event. It makes one mark in one place. There is no half photons splashing across the screen. Yet if many photons are sent through the experiment one after another, the individual marks slowly build into an interference pattern. Even when the photons are so spread out at time that only one is in the apparatus at once, the final pattern still looks like the result of wave interference. The same kind of behavior appears with electrons. Send electrons through two slits one at a time, and each electron is detected at a particular spot. But after many electrons have been recorded, the familiar interference pattern emerges. This is where the matter wave idea becomes impossible to treat as only a decorative metaphor. The electron is not merely a little pellet taking a hidden route, while scientists fail to keep up. Its quantum behavior produces the measurable pattern associated with waves. This does not mean an electron physically splits in half like a tiny confused pea and squeezes through both slits in the everyday sense. It means that the quantum state evolves in a way that includes the possibilities associated with both paths. Those possibilities can interfere. The mathematics predicts where detections are likely to appear, and over many repeated trials, those probabilities become visible as the pattern on the screen. One result at a time looks particle-like. The overall distribution looks wave-like. The two sides of quantum behavior sit in the same experiment, politely refusing to be separated. The experiment becomes even more revealing when measurement enters the story. If a detector is placed near the slits to find out which slit the photon or electron passes through, the interference pattern disappears. Instead of a wave-like series of bands, the result becomes more like two particle-like groups. The phrase often used here is which path information. If the experiment makes it physically possible to know which path the quantum object took, the interference between the alternatives is lost. This point is often misunderstood. The double-slit experiment does not show that particles have tiny minds, or that they become shy when someone looks at them. An electron is not peeking nervously at the laboratory door. In quantum physics, measurement is not about human attention in a mystical sense. It is about physical interaction. To obtain which path information, the quantum system must interact with a detector, or with light, or with some part of the environment in a way that changes the available information and the behavior of the system. What matters is not a conscious observer staring dramatically at the apparatus, but the physical fact that the alternatives have become distinguishable. That distinction is important because it keeps the mystery honest. The double-slit experiment is strange enough without adding unnecessary magic to it. Quantum mechanics says that interference appears when the alternatives remain part of a coherent quantum description. If the path information becomes available, that coherence is disrupted, and the interference pattern vanishes. The experiment therefore reveals a deep connection between probability, information, and measurement. This is why the double-slit experiment remains so central to understanding quantum physics. It shows that wave-like probability is not just an abstract mathematical convenience. It creates visible, measurable patterns. It shows that electrons and photons cannot be fully understood as ordinary particles following one definite classical path all along. It also shows that measurement is not a passive act of simply uncovering a pre-existing story in the familiar way. At the quantum scale, what can be measured, what information exists, and what pattern appears are tied together. The lesson is simple to state, but difficult to picture. A quantum object can arrive as a single detection, yet the pattern of many detections can be shaped by wave-like interference. Matter can behave like a wave without becoming an ordinary ripple. Light can behave like particles without giving up its wave behavior, and the question of which path was taken is not a minor detail. It can decide whether the universe writes two broad marks on a screen, or a delicate striped pattern that quietly announces the presence of quantum possibility. The double-slit experiment leaves behind a very natural question. If an electron is not simply a tiny pellet slipping through one opening or the other, and if its behavior can create an interference pattern before any definite detection appears, then what exactly is being described before the measurement happens? Quantum mechanics answers with one of its most important ideas, the wave function. The wave function is the central mathematical object in quantum mechanics. It describes the state of a quantum system. That system might be a single electron, a photon, an atom, or a more complicated arrangement of particles. The wave function is not a little cloud of mist floating in space, and it is not a tiny physical wave in the same sense as a ripple on water. It is a mathematical description that allows physicists to calculate the probabilities of different measurement outcomes. It tells what can be predicted, how likely certain results are, and how the quantum state changes when it is not being measured. This is where quantum physics becomes both more precise and more unfamiliar. In ordinary life, probability often means incomplete knowledge. If a coin is covered by a hand, it is already heads or tails, even if nobody has looked yet. The uncertainty belongs to the person, not to the coin. The coin has a definite state, and the observer simply does not know it. Classical physics usually works in a similar spirit. If a planet has a position and velocity, those properties are definite, whether or not anyone measures them perfectly. In principle, better information means better prediction. Quantum probability is different. In quantum mechanics, the theory does not always assign definite classical properties to every measurable quantity before measurement. An electron does not necessarily have a precise position in the same way a marble has a place on a table. Before measurement, the wave function gives a spread of possibilities. It can describe where the electron may be detected and with what probability, but it does not always describe a small classical object following one definite hidden path. This idea was given powerful mathematical form by Erwin Schrödinger. In the mid-1920s, Schrödinger developed wave mechanics, a version of quantum theory built around the wave function. His famous Schrödinger equation describes how the wave function changes over time. In gentle terms, it is the rule for how quantum possibility evolves when a system is left alone. It allows the wave function to spread, shift, oscillate, interfere and develop in a smooth and predictable mathematical way. That last point is worth holding on to carefully. Quantum mechanics is often described as uncertain, and that is true in an important sense. But the wave function itself does not usually evolve randomly. When no measurement is taking place, Schrödinger's equation gives a precise rule for its development. The uncertainty appears when the wave function is connected to actual measurement outcomes. The theory can say exactly how probabilities evolve, even when it cannot say in advance which single result will appear in an individual measurement. The equation itself can be written in different forms depending on the system being studied. For a simple particle, it connects the particle's energy to changes in its wave function. Spoken out in plain language, the idea is this: the total energy of a quantum system determines how its wave function changes through time. That is not the full mathematical detail, of course, but it captures the role of the equation without turning the night into an ambush by symbols. Schrödinger's wave mechanics was not the only version of quantum theory being developed. Werner Heisenberg had created matrix mechanics, which looked very different mathematically but gave the same physical predictions. This was one of those moments in science where nature seemed to accept two different pieces of paperwork, provided the final answers were correct. Over time, physicists understood that these approaches were equivalent descriptions of the same underlying theory, but the wave function still needed interpretation. What did it mean physically? Was it a real wave, a tool for calculation, a description of knowledge, a description of something deeper? One of the crucial answers came from Max Born. Born proposed the rule that connects the wave function to probability. This became known as the Born rule. It says in essence that the wave function is used to calculate the probability of obtaining different measurement results. More specifically, the Born rule tells physicists how to get the probability of finding a particle in a particular place, or measuring some other value from the wave function. In clear-spoken form, the key idea is the probability of a measurement result is found from the wave function's amplitude multiplied by its corresponding amplitude. In ordinary mathematical language, this involves the square of the wave function's magnitude. But for voiceover, the important point is that the wave function is not itself the probability. It is a deeper quantity from which probabilities are calculated. This may sound like a small distinction, but it matters. The wave function contains what are called probability amplitudes. These amplitudes can combine, cancel, and reinforce each other. That is why quantum systems can show interference. Ordinary probabilities do not usually cancel each other out. If there is a chance of rain from one weather pattern and a chance of rain from another, the two chances do not politely erase each other, because they are out of phase. Weather is complicated, certainly, but it is not doing quantum choreography in the clouds. Quantum amplitudes, however, can interfere, and that interference changes the probabilities that appear when measurements are made. This is the key to understanding the double-slit experiment more clearly. When an electron passes through the double-slit arrangement without which path information being available, its wave function includes the alternatives associated with both slits. The probability amplitudes connected with those alternatives can interfere. In some places on the screen, the amplitudes reinforce one another, making detections more likely. In other places, they cancel, making detections less likely or nearly absent. Over many repeated electrons, this pattern becomes visible as bright and dark bands, or as regions with many detections and regions with few. So the interference pattern does not come from a tiny classical pellet, secretly splitting into two pieces and performing a miniature acrobatic routine behind the barrier. It comes from the structure of the wave function. Each detection is definite. An electron is found at one particular spot, but the pattern built by many detections reflects the wave function's probability structure. The single event is particle-like, the distribution is wave-like. Quantum mechanics holds these together without forcing either one to behave like an everyday object. Measurement then introduces the sharp contrast. Before measurement, the wave function can be spread out across many possible positions. It can pass through both paths in the sense that the quantum state includes both alternatives. It can interfere with itself, but when a position is measured, the result is definite. The electron is detected here, not everywhere at once. The measuring screen records a spot. The laboratory notebook gets one entry. Nature does not hand over a gentle smear and ask the physicist to interpret the mood. This difference between smooth wave function evolution and definite measurement outcomes is one of the central tensions of quantum mechanics. The wave function evolves according to Schrödinger's equation, spreading and interfering in a controlled mathematical way. Measurement gives one result. The Bohr rule tells the probabilities of those results. It does not usually tell which exact result will happen in a single trial. That single outcome remains unpredictable, even though the overall pattern can be predicted with extraordinary accuracy. And that is why quantum probability is so powerful. It is not a confession of scientific failure. It is not scientists shrugging at the universe because the equipment had a difficult morning. Quantum probability is built into the theory, and the theory works with astonishing precision. It predicts atomic spectra, chemical bonds, semiconductor behavior, lasers, magnetic resonance imaging, and countless laboratory results. The probabilities are not vague guesses. They are calculated from the wave function, and experiments confirm them again and again. The wave function, therefore, sits at the heart of quantum physics, because it carries the information that classical pictures cannot hold. It describes possibilities before measurement. It evolves smoothly. It allows interference. It connects to probabilities through the Bohr rule. It explains why quantum systems can act wave-like in one arrangement and particle-like in another. It does not make the universe less lawful. It reveals that the laws are written in a language of amplitudes, probabilities, and measurement outcomes rather than tiny definite paths traced through space. So when the double-slit experiment creates its delicate pattern, the wave function is the quiet mathematics underneath it. It is not a decorative idea added later to make the experiment sound more mysterious. It is the thing that makes the pattern understandable. The electron is not a miniature marble with a secret root. It is a quantum system described by a wave function, and that wave function gives rise to the probabilities that appear, one small detection at a time, until the hidden order becomes visible on the screen. The wave function gives quantum physics a language of possibility, but it also leads to one of the most famous ideas in all of science, Heisenberg's uncertainty principle. It is often described as though it means the universe is blurry because human beings are bad at measuring things. That is not quite right. The uncertainty principle is not mainly a story about shaky hands, dusty instruments, or a scientist leaning too close to the apparatus after too much coffee. It is a deeper statement about what can be sharply defined in nature itself. Werner Heisenberg introduced the uncertainty principle in the late 1920s during the early development of modern quantum mechanics. It applies especially to pairs of physical properties that are connected in a particular mathematical way. The most famous pair is position and momentum. Position simply means where something is. Momentum means how much motion it has, combining how massive something is with how fast it is moving and in what direction. In everyday life, both seem perfectly reasonable. A thrown ball has a place, and it has motion. A car on a road has location, a speed, and a direction. With good enough tools, it feels as though both could be known as accurately as anyone likes. At the quantum scale, the situation changes. The uncertainty principle says there is a precise limit to how well certain pairs of properties can be simultaneously defined. If the position of a particle is made very sharply defined, then its momentum becomes less sharply defined. If its momentum is made very sharply defined, then its position becomes more spread out. This is not because the measuring device has failed. It is because quantum objects are described by wave functions, and wave functions have a wave-like structure. A useful way to approach this is through waves themselves. Imagine a perfectly regular wave stretching on, with the same spacing between each crest. Because the wave repeats so neatly, it has a well-defined wavelength. In quantum mechanics, wavelength is linked to momentum through Louis de Broglie's matter wave idea. So a wave with a very clear wavelength corresponds to a particle with a very clear momentum, but there is a cost. If the wave stretches smoothly across a huge region, it is hard to say exactly where the particle is. The position is not sharply localized. Now imagine trying to make the particle's position much more definite. To do that, the wave function must be packed into a smaller region, forming what is called a wave packet. A wave packet is a concentrated bump of wave-like behavior, localized enough to say the particle is probably somewhere within a particular area. But making such a packet requires mixing together many different wavelengths. Once many wavelengths are involved, the momentum is no longer sharply defined. The particle's position becomes clearer, but its momentum becomes more uncertain. This is the heart of the uncertainty principle. A sharply localized wave requires a spread of wavelengths. A sharply defined wavelength requires a spread-out wave. Position and momentum are tied together through the structure of the wave function itself. Quantum uncertainty is therefore not a fog placed over a hidden classical reality by bad equipment. It arises from the way quantum states are built. The formal uncertainty relation connects the uncertainty in position with the uncertainty in momentum, and the limit is set by Planck's constant. In voiceover terms, the principle can be expressed like this. The uncertainty in position multiplied by the uncertainty in momentum cannot be smaller than a fixed tiny amount set by Planck's constant. Because Planck's constant is extremely small, this limit is usually invisible in everyday life. A tennis ball can have its position and momentum known so well that no human observer notices any quantum restriction. At the scale of electrons, atoms and photons, however, the restriction becomes unavoidable. This is why the uncertainty principle does not mean ordinary reality is loose or chaotic. It does not mean a mountain might suddenly decide to become a cloud because uncertainty, which would be inconvenient for hikers and estate agents alike. It does not mean anything can happen. Quantum mechanics is filled with rules, and the uncertainty principle is one of them. It places limits on what can be simultaneously defined, but those limits are precise. They are not permission slips for nonsense. They are part of the mathematical structure that makes quantum mechanics so accurate. Another common misunderstanding is that uncertainty is caused simply by disturbing the particle during measurement. There is a related idea here, because measuring a tiny system often does involve interacting with it. To observe an electron, for example, some physical process must connect the electron to a detector. That interaction can change the system. But the uncertainty principle goes deeper than this measurement disturbance picture. Even before any particular measurement is made, the wave function may not contain a sharply defined value for both position and momentum at the same time. This is where the idea links directly back to probability. In classical physics, probability often means ignorance. A hidden object has a definite place, even if nobody knows it. A moving object has a definite speed, even if nobody has measured it well. In quantum mechanics, the wave function does not always describe definite classical properties waiting quietly behind the curtain. It describes a quantum state, and some properties may be spread across possible values in a fundamental way. Heisenberg's uncertainty principle therefore changes what it means to describe a physical system. The world is not merely difficult to measure at tiny scales, it is organized differently. The wave function can provide a precise description, but that description is not always a list of exact classical facts. It may instead contain a probability distribution for position, a probability distribution for momentum, and a fixed relationship between how sharply those distributions can both be defined. This is one reason quantum physics feels so different from the older clockwork universe. Classical determinism imagined that objects had precise positions and motions, even if human beings lacked perfect knowledge. Quantum mechanics says that, for certain pairs of properties, nature does not always supply those precise values together in the old classical sense. There are limits built into the fabric of the theory, not because physics has become careless, but because the quantum state itself has a wave-like form. And once that is understood, the uncertainty principle becomes less like a mysterious warning and more like a quiet rule of structure. A particle is not a tiny bead with every property neatly labelled in advance. It is a quantum system described by a wave function. That wave function can be narrow in place or narrow in momentum, but not both without limit. The uncertainty is not a flaw in knowledge. It is part of the shape of what can be known, what can be defined, and how deeply the universe differs from the smooth certainty of everyday intuition. Superposition is one of the most famous ideas in quantum physics, and also one of the easiest to exaggerate. It is often described as if a particle is somehow doing everything possible at once, with the enthusiasm of a very tiny overachiever. But the real idea is more precise and much more useful. In quantum mechanics, superposition means that a system can be described by a combination of possible states before a measurement gives one specific outcome. A quantum state is not always limited to one definite classical option. An electron, photon, atom, or other quantum system can exist in a state that combines several possible measurement results. These possibilities are not vague guesses. They are described by probability amplitudes, the deeper quantities used by the wave function to calculate measurement probabilities. When a measurement is made, only one definite result is obtained, but before that measurement, the quantum state may genuinely contain a structured combination of possible outcomes. Electron spin gives one of the clearest examples. Spin is an intrinsic quantum property, not a little ball rotating like a planet. When measured along a chosen direction, an electron can give one of two possible results. These are often described as spin up and spin down, though those names should not be imagined too literally. Before measurement, the electron's spin state can be a superposition of those possibilities. The quantum state does not have to say, in the old classical way, that the electron is definitely one or definitely the other. It can contain a combination of both possible outcomes, with precise rules for the probabilities. Photon polarization offers another useful example. Light can be polarized, meaning its electromagnetic behavior has a particular orientation. A photon can be prepared in a polarization state that is not simply one measurement outcome or another, but a combination of possible outcomes relative to a chosen measuring device. When the photon meets a polarizing filter, one definite result appears. It passes through, or it does not. But before that interaction, its quantum state may be described as a superposition relative to the measurement being performed. Atoms can also occupy superpositions of energy states. An atom might be described by a combination of being in one energy level and another, until interaction with a measuring process or environment leads to a definite result. This is not just a philosophical curiosity. Superpositions of atomic states are used in real physics, including atomic clocks, spectroscopy, quantum information experiments, and precision measurement. The theory may sound dreamlike, but the laboratory behavior is extremely practical. The important point is that superposition does not mean an everyday object is literally doing every imaginable thing at once in a cartoonish way. It does not mean a chair is simultaneously in the kitchen, on the moon, and applying for a modest administrative role. Large objects are made of enormous numbers of particles interacting constantly with their surroundings, and their quantum effects are usually hidden by environmental interactions. Superposition is real, but it must be understood within the careful rules of quantum states, not through wild everyday exaggerations. One reason superposition works mathematically is the principle of linearity. In plain language, if one quantum state is allowed and another quantum state is allowed, then certain combinations of those states are also allowed. Quantum states can be added together to form new possible states. This is one of the basic structural features of quantum mechanics. It is what allows the wave function to describe combinations of possibilities and what allows probability amplitudes to interfere. Paul Dirac played a major role in making this language clearer and more powerful. Dirac helped develop the mathematical formulation of quantum mechanics, including a precise notation for quantum states that made superposition, measurement, and probability easier to handle. His work connected different versions of quantum theory and helped shape the formal structure still used by physicists today. Dirac's notation can look spare and elegant on a blackboard, though admittedly less soothing if encountered suddenly at midnight without warning. Superposition also connects directly with the uncertainty principle. Quantum systems often resist being assigned one definite classical description before measurement. That does not happen because the theory is vague, or because physicists have chosen to be mysterious for dramatic effect. It happens because the structure of the quantum state is different from the structure of an ordinary classical object. A wave function can contain multiple possible outcomes, and different measurable properties can be related in ways that prevent them all being sharply defined at once. This is why superposition should be treated with both wonder and restraint. It is not a license to claim that anything and everything is happening simultaneously. It is a precise statement about how quantum states are built. A system can be described by a combination of possible states, and the probabilities of later measurement outcomes are determined by the amplitudes within that state. When a measurement happens, the result is definite. The detector clicks in one place. The photon passes or does not pass through the filter. The atom is found in one energy state rather than another. But before that result appears, quantum mechanics describes the system through a richer structure than classical physics allowed. Superposition is that richer structure. Not chaos, not magic, but a carefully defined combination of possibilities at the heart of the quantum world. Superposition gives quantum physics its strange landscape of possibilities. A system can be described by a combination of possible states, each with its own probability amplitude, until a measurement gives one definite result. But that sentence hides one of the deepest puzzles in the whole theory. If the wave function can spread, combine, and evolve smoothly, why does the world we observe arrive as single outcomes? This is the measurement problem. It is the question of how a quantum system described by a spread of possibilities produces one actual result when it is measured. Before measurement, an electron may be described by a wave function spread across different possible positions. A photon may be in a superposition of possible polarizations. An atom may be in a combination of energy states. But when a detector records the event, it does not usually report a soft menu of maybes. It gives one result. The electron is found here. The photon passes through the filter. The atom is measured in this energy state rather than that one. The difficulty comes from the contrast between two kinds of behavior in quantum theory. When a quantum system is not being measured, the wave function evolves according to the Schrödinger equation. That evolution is smooth, continuous, and mathematically predictable. The wave function can spread out, overlap with itself, and produce interference. Its probability amplitudes can reinforce or cancel, shaping the chances of later outcomes. Nothing in that smooth evolution, by itself, obviously explains why one specific result appears when measurement happens. Yet real measurements do produce specific results. A screen in the double-slit experiment records one dot at a time. A Geiger counter clicks or does not click. A detector gives a definite reading. In the laboratory, nobody opens the notebook and writes, "The electron was feeling broadly distributed today." The result is one result. The mystery is how the smooth evolution of the wave function connects to that sudden definiteness. This does not mean quantum mechanics fails as a practical theory. Quite the opposite. It predicts measurement probabilities with extraordinary accuracy. The Bohr rule tells physicists how to calculate the likelihood of different outcomes from the wave function. Repeated experiments then match those predictions again and again. The puzzle is not that quantum mechanics gives bad results. The puzzle is what the theory is telling us about reality between preparation and measurement, and what exactly counts as a measurement in the first place. One historically influential way of speaking about this problem is the Copenhagen interpretation, associated especially with Niels Bohr and Werner Heisenberg. The Copenhagen interpretation is not one single perfectly fixed doctrine, because different physicists have used the phrase in slightly different ways. But broadly, it emphasizes that quantum mechanics predicts the outcomes of measurements, and that the experimental arrangement matters deeply in defining what can be said about a system. It treats the wave function as a tool for calculating possible results, while measurement brings about a definite outcome. Bohr was especially careful about the role of measuring devices and experimental context. He argued that quantum phenomena cannot be separated from the conditions under which they are observed. Heisenberg, meanwhile, helped develop the idea that quantum properties are not simply classical properties, waiting patiently to be uncovered. Together, their view shaped the early language of quantum measurement, even though not every physicist found that language satisfying. Albert Einstein remained deeply uncomfortable with aspects of quantum theory, especially its apparent reliance on probability and its refusal to provide a fully classical picture of underlying reality. Erwin Schrödinger also questioned how the theory was being interpreted. His most famous challenge came through the thought experiment now known as Schrödinger's cat. The setup is deliberately unsettling. A cat is imagined inside a sealed box with a quantum event, such as the possible decay of a radioactive atom, connected to a mechanism that could release poison. If the atom decays, the cat dies. If it does not, the cat lives. Quantum mechanics can describe the radioactive atom as being in a superposition of decayed and not decayed before measurement. If that superposition is applied directly to the entire box, then the cat seems to become entangled with the atom, leaving the combined system in a strange superposition of alive and dead. Schrödinger did not introduce this idea because he thought cats made charming mascots for physics, or because he wanted future generations to place unfortunate cartoon cats on coffee mugs. The point was critical. He wanted to expose the strange consequences of applying quantum superposition too simply to large everyday objects. A cat is not observed as both alive and dead. When the box is opened, there is one definite outcome. So what exactly happens between the quantum possibilities and the definite result? That is the heart of the measurement problem. The real question is not whether superpositions exist mathematically. Quantum theory uses them successfully, and experiments confirm their effects in systems such as electrons, photons, atoms, and superconducting circuits. The deeper question is how those quantum possibilities relate to the definite world observers experience. This is why measurement sits at the center of quantum foundations. It asks how probability becomes actuality, how wave function evolution relates to observation, and why the world appears definite even though its underlying description can involve many possible outcomes. Quantum mechanics gives stunningly accurate rules, but the meaning of those rules remains subtle. The ordinary world is filled with definite things. A lamp is on or off. A detector is clicked or not clicked. A cat, thankfully, is not treated in daily life as a philosophical fog with whiskers. But quantum theory shows that beneath that definiteness lies a stranger structure. Superposition describes possible outcomes. Measurement gives one result. And between those two statements sits one of the quietest and most persistent mysteries in modern physics. The measurement problem shows how strange quantum probability can be. But quantum physics is not only about what happens when a detector gives an answer. Sometimes, those probabilities reach into places that classical physics would treat as forbidden. One of the clearest examples is quantum tunneling. In classical physics, a barrier is usually straightforward. If a ball does not have enough energy to roll over a hill, it rolls part way up, slows down, and comes back. It does not quietly appear on the other side with the innocent expression of something that definitely followed the rules. A wall blocks a thrown object. A hill stops a slow ball. A barrier is a barrier, and if the energy is too low, the journey ends. At the quantum scale, the story changes. Quantum tunneling is the phenomenon where a particle has a probability of being found beyond a barrier, even when classical physics says it does not have enough energy to cross it. This does not mean the particle has secretly climbed over the barrier in the ordinary sense. It means the wave function, which describes the particle's quantum state, does not always stop sharply at the edge of a forbidden region. The wave function can extend into a barrier. Usually it becomes smaller as it does so, meaning the probability decreases. If the barrier is too wide or too strong, the chance of finding the particle on the far side may be incredibly tiny. But if the barrier is thin enough, or the conditions are suitable, part of the wave function can extend through the barrier, leaving a real probability that the particle will be detected beyond it. The particle has not broken the rules. It is obeying different rules. This is one of the important lessons of quantum physics. A particle is not simply a tiny hard object with a definite path at every moment. It is described by a wave function, and the wave function determines the probabilities of possible measurement outcomes. If that wave function reaches beyond a barrier, then the particle may sometimes be found there. Classical intuition says no. Quantum mechanics says rarely, perhaps, but not never. One of the most important examples is alpha decay. In certain radioactive nuclei, an alpha particle can escape from the nucleus even though, classically, it appears trapped by a barrier created by the nuclear forces and electric repulsion involved. The alpha particle does not seem to have enough energy to simply climb out. Yet radioactive decay happens, and alpha particles are emitted. George Gamow helped explain this in the late 1920s by applying quantum tunneling to alpha decay. His work showed that the alpha particle could be described by a wave function, with a probability of tunneling through the nuclear barrier. This gave physics a way to understand how particles could escape from atomic nuclei without needing enough classical energy to go over the barrier. The result helped connect radioactive decay to the new quantum theory in a precise and powerful way. Tunneling is also central to one of the most remarkable instruments in modern science, the scanning tunneling microscope. This device was developed by Gerd Binnig and Heinrich Rohrer at IBM Zurich in the early 1980s. It uses a sharp conducting tip brought extremely close to a surface. The tip does not physically scrape across the atoms like a tiny rake, which is good, because atoms are not fond of heavy-handed gardening. Instead, electrons can tunnel between the tip and the surface when the gap is small enough. The amount of tunneling current depends very sensitively on the distance between the tip and the surface. By scanning the tip across the material and measuring changes in this current, scientists can map the surface at the scale of individual atoms. This made it possible to image and study surfaces with extraordinary detail. The scanning tunneling microscope turned a strange quantum effect into a practical tool for seeing the atomic world. Tunneling also appears in semiconductor devices. Semiconductors are the materials at the heart of modern electronics, including transistors and computer chips. In these tiny structures, electrons move through regions where quantum effects matter. Sometimes tunneling is useful, as in certain specialized devices. Sometimes it creates limits, because as electronic components become extremely small, electrons can tunnel through barriers that engineers would prefer them not to cross. At that scale, the universe begins gently ignoring the walls in the circuit diagram. The key point is that tunneling is not a fantasy doorway or a magical shortcut. It is a measurable consequence of the wave function. Quantum probability is not merely an abstract idea used to discuss uncertain measurements. It has physical effects. It shapes radioactive decay. It allows microscopes to image atoms. It influences the behavior of electronic devices. It appears in nuclear processes, materials, and technologies that depend on the rules of the microscopic world. So quantum tunneling deepens the connection between probability and reality. A wave function can extend where a classical particle could not go. A small probability can become a real event. And when many particles are involved, or when the right conditions are carefully engineered, the probability can become a powerful scientific tool. Classical physics would expect barriers to be firm, final, and absolute. Quantum physics shows that at small scales barriers can be more subtle. They still matter. They still reduce the chance of passage. But they do not always end the story. Beneath the smooth surface of ordinary experience, nature allows possibilities to fade, stretch, and sometimes appear on the other side. Quantum tunneling showed that particles do not always behave like tiny solid objects moving through simple barriers. But another quantum property goes even deeper into the structure of matter. It helps explain why atoms are built the way they are, why the periodic table has its shape, and why ordinary objects do not collapse into a single dense blur. That property is called spin. Spin is one of those words that can be slightly misleading, because it sounds as if an electron is a tiny ball rotating on its axis, like a microscopic planet with a very intense schedule. But quantum spin is not ordinary spinning. It is an intrinsic quantum property of particles. Intrinsic means it belongs to the particle itself, rather than being caused by some visible motion through space. An electron has spin in the way it has electric charge or mass. It is part of what the electron is. Spin becomes noticeable through measurable effects, especially magnetic behavior. Electrons act as if they have tiny magnetic properties. When placed in magnetic fields, their spin affects how they behave. One of the most important demonstrations of this came from the Stern-Gerlach experiment, carried out by Otto Stern and Walter Gerlach in the early 1920s. They sent a beam of silver atoms through a non-uniform magnetic field and observed that the beams split into distinct parts rather than spreading smoothly. This was surprising. A classical picture might suggest that the atoms could have magnetic orientations at any angle, producing a continuous smear on the detector. Instead, the results appeared in discrete outcomes. The experiment showed that certain angular momentum properties in quantum systems are quantized. In simpler terms, when measured in a particular direction, spin-related behavior does not come in every possible value. It gives specific allowed results. For electrons, spin is especially important inside atoms. Electrons have two possible spin outcomes when measured along a chosen direction, often called spin up and spin down. Those names are convenient, but they should not be taken too literally. The electron is not a tiny arrow that was definitely pointing up all along in the everyday sense. It is a quantum system, and spin is one of the properties that can be measured according to quantum rules. This leads to one of the most important principles in all of physics, the Pauli exclusion principle. Wolfgang Pauli introduced it in 1925. The principle says that identical fermions cannot occupy exactly the same quantum state at the same time. Electrons are fermions, so this rule applies to them. Two electrons in the same atom cannot have every quantum property identical. If they share the same region and energy arrangement, they must differ in some other allowed quantum property, such as spin. This may sound like a technical detail, but it quietly builds the visible world. Without the Pauli exclusion principle, electrons in atoms would not arrange themselves into structured shells and orbitals in the same way. They could all collapse into the lowest available state, and chemistry would be unrecognizable. Instead, electrons fill available quantum states in an ordered pattern. This pattern helps create the structure of atoms and gives the periodic table its repeating form. The periodic table is not just a chart that chemistry students are asked to befriend under exam conditions. It is a map of quantum structure. Elements behave differently because their atoms contain different numbers of protons and electrons, and because those electrons occupy quantum states in organized ways. The outer electrons, often called valence electrons, play a major role in chemical bonding. The reason sodium behaves differently from neon, or carbon differently from oxygen, is rooted in quantum rules governing electron arrangement. The Pauli exclusion principle also helps explain why matter takes up space. Ordinary objects feel solid not because atoms are tiny hard marbles touching edge to edge, but because electrons are governed by quantum states in electromagnetic interactions. When atoms are pushed close together, their electron states cannot simply all become identical. The exclusion principle resists that compression. Along with electric repulsion between charged particles, this gives matter much of its familiar solidity. A hand does not pass through a table because the quantum and electromagnetic structure of atoms says, very politely but very firmly, no. Spin also helps separate particles into two broad families, fermions and bosons. Fermions include particles such as electrons, protons and neutrons, and they obey the Pauli exclusion principle. They are the matter-building particles, the ones that stack into structured arrangements rather than all piling into the same state. Bosons, by contrast, can share the same quantum state. Photons are bosons, which is part of why laser light can involve many photons acting in a highly coordinated way. Satyendranath Bose helped develop the statistics that describe bosons, and Paul Dirac contributed deeply to the quantum theory of particles, spin, and the distinction between these families. This distinction between fermions and bosons is one of the quiet organizing principles of the universe. Fermions help build matter with structure, separation, and variety. Bosons often act as force carriers or collective participants in quantum behavior. The names may sound technical, but the consequence is wonderfully direct. The world has shape because particles do not all follow the same social rules. Some refuse to share the same quantum state. Others are perfectly happy to gather together. Spin and the Pauli exclusion principle therefore connect the abstract language of quantum mechanics to the ordinary world with remarkable force. They explain why atoms have structure, why energy levels fill in patterns, why the periodic table repeats, and why chemistry exists in its familiar richness. Quantum rules do not merely describe tiny particles hidden far away from daily life. They build the furniture of reality. The atom is stable not because it is a miniature solar system, and matter is solid not because particles are little billiard balls pressed together. The deeper explanation lies in quantum states, spin, exclusion, charge, and probability. Underneath every object that seems calm and continuous, electrons are arranged according to rules that have no true classical equivalent. The shape of matter is not an accident. It is quantum physics made visible. The structure of atoms leads naturally into chemistry, because chemistry is what happens when atoms meet, share, exchange, attract, repel, rearrange, and occasionally behave like tiny social networks with stricter rules. Every chemical reaction, every bond, every molecular shape, and every material property depends on the quantum behavior of electrons. Chemistry is not separate from quantum physics. It is one of the places where quantum physics becomes visible as water, salt, sugar, stone, air, protein, glass, and life. The key players are electrons. In older pictures of the atom, electrons were sometimes imagined as little planets moving around the nucleus in neat circular orbits. That image can be useful as an early stepping stone, but it is not the modern quantum picture. Electrons in atoms are described by orbitals. An atomic orbital is not a track. It is not a fixed path. It is a probability distribution, meaning a region around the nucleus where an electron is likely to be measured. This matters because orbitals have shapes, energies, and rules. Some orbitals are roughly spherical, others have dumbbell-like shapes. More complicated ones can look rather like nature became briefly interested in abstract sculpture. These shapes are not decorative. They affect how atoms bond, how molecules form, and what arrangements are stable. The electron is not simply travelling around the nucleus like a tiny moon. Its wave function gives a structured probability pattern, and chemistry grows from those patterns. The Pauli exclusion principle is central here. Because electrons are fermions, identical electrons cannot occupy exactly the same quantum state. This rule helps determine how electrons fill atomic orbitals. Electrons arrange themselves into shells and subshells, according to allowed quantum states, energy levels, and spin. That arrangement creates the periodic table, and once the periodic table exists, chemistry follows. The outer electrons of an atom, often called valence electrons, are especially important. These are the electrons most involved in bonding. Atoms with similar outer electron arrangements often behave in similar chemical ways, which is why elements in the same column of the periodic table tend to share chemical patterns. The repeating structure of the periodic table is therefore not just a convenient layout for classrooms. It is a visible map of quantum electron arrangement. One of the most important forms of bonding is covalent bonding. In a covalent bond, atoms share electrons. A simple example is the hydrogen molecule, where two hydrogen atoms form a stable molecule by sharing their electrons in a way that lowers the overall energy of the system. But the phrase sharing electrons should not be pictured too casually. as if atoms are politely passing tiny beads back and forth across a microscopic table. The deeper explanation involves overlapping wave functions, allowed quantum states, electron probability, electric attraction, and energy minimization. Energy minimization is a major theme in chemistry. Systems tend to settle into arrangements with lower energy when the rules allow it. When atoms form a chemical bond, the combined arrangement of nuclei and electrons can have lower energy than the separated atoms. The positive nuclei attract the negatively charged electrons. The electrons repel one another, the nuclei repel one another, and quantum rules determine which electron arrangements are possible. A stable bond appears when all of those effects balance in a way that lowers the total energy. Linus Pauling played a major role in developing modern ideas about chemical bonding. His work helped connect quantum mechanics with molecular structure, showing how bonds, orbital hybridization, electronegativity, and molecular shape could be understood using quantum principles. Pauling's book, The Nature of the Chemical Bond, became one of the most influential scientific works of the 20th century. It helped make clear that chemistry's familiar rules had a deeper quantum foundation. Water is a good example of this. A water molecule contains oxygen bonded to two hydrogen atoms. Its bent shape is not random. It comes from the arrangement of electrons around the oxygen atom and the way quantum states guide bonding geometry. That bent shape gives water its polarity, meaning one side of the molecule carries a slight negative character and the other carries a slight positive character. From that small quantum-rooted structure comes hydrogen bonding, surface tension, ice floating on liquid water, and many of the properties that make water so important for life. Carbon dioxide shows another molecular shape. It is a linear molecule with carbon bonded to two oxygen atoms. Its shape and bonding depend on electron arrangement and orbital structure. Table salt, or sodium chloride, works differently again. It is not mainly covalent. Sodium tends to lose an electron, and chlorine tends to gain one, forming charged ions that arrange into a crystal lattice through electric attraction. Even here, quantum physics sits underneath the pattern, because the tendencies of sodium and chlorine come from their electron configurations. In living things, quantum chemistry becomes even richer. The bases in DNA have specific molecular structures that allow them to pair in reliable ways. Proteins fold according to chemical interactions between atoms and groups of atoms. Enzymes guide reactions by shaping energy landscapes at the molecular scale. None of this requires saying that life is mystical in a vague quantum sense. It simply means that the chemistry of life depends on the same quantum rules as every other form of chemistry. So quantum physics does not remain hidden in distant laboratories. It is present whenever atoms form molecules, whenever a flame burns, whenever food cooks, whenever a battery works, whenever a medicine binds to a protein, and whenever DNA carries information inside a cell. The rules of spin, orbitals, energy levels, wave functions, and the Pauli exclusion principle become the structure of substances. Chemistry is the everyday language of quantum physics. It is what happens when the strange rules of electrons become the familiar behavior of materials. The periodic table builds the alphabet. Bonds build the words. Molecules build the sentences. And from those quiet quantum arrangements, the ordinary world becomes solid, colourful, reactive, fragrant, useful, and alive. Chemistry shows how quantum rules build familiar substances, but one of the strangest quantum ideas appears when systems are linked so deeply that they cannot be fully described as separate things. This is quantum entanglement. It is a relationship between quantum systems where the state of each part depends on the state of the whole, even when the parts are separated by distance. In ordinary life, objects usually have their own independent properties. A pair of gloves can be placed into two boxes. One box travels to London, the other to Tokyo. If someone opens the London box and finds the left-hand glove, they instantly know the other box contains the right-hand glove. Nothing mysterious has happened. The gloves had definite identities all along. The discovery only revealed information that was already fixed. Quantum entanglement is subtler than that, and much less willing to behave like well-organized winter clothing. In an entangled quantum system, the combined state can be definite even when the individual parts do not have separate definite properties before measurement. For example, two particles might be prepared so that a certain property, such as spin, is connected between them. When one particle is measured, the result is correlated with the result that will be found for the other particle. The two outcomes are linked, but quantum mechanics does not treat this as simply uncovering two pre-written labels hidden inside the particles from the beginning. This deeply bothered Albert Einstein. In 1935, Einstein, Boris Podolsky, and Nathan Rosen published a famous argument now known as the EPR argument. They were not trying to prove that quantum mechanics was useless. They recognized its success, but they questioned whether it was complete. Their argument suggested that if quantum mechanics allowed strong correlations between distant systems, then perhaps the theory was missing some deeper description of reality. Einstein was especially uncomfortable with what he later called spooky action at a distance. The concern was not theatrical. It touched one of the deepest ideas in physics: locality. Locality is the principle that objects are directly influenced by their immediate surroundings, and that effects should not travel faster than light. Einstein's special relativity had made the speed of light a cosmic limit for signals and causal influence. So if measuring one particle seemed connected to the state of another faraway particle, Einstein wanted to know what was really going on. Was quantum mechanics incomplete? Were there hidden variables, unseen properties that determined the results in advance? Or did nature genuinely refuse to fit the old picture? Niels Bohr responded to the EPR argument almost immediately. His reply was not that Einstein had made a simple mistake. The disagreement was more serious than that. Bohr argued that quantum properties cannot be discussed apart from the experimental conditions under which they are measured. In his view, the EPR argument underestimated how deeply measurement context matters in quantum theory. For Bohr, quantum mechanics was not incomplete simply because it refused to provide the kind of classical hidden picture Einstein wanted. It was revealing a different kind of physical description. For decades, this debate seemed partly philosophical. Quantum mechanics worked, but the question remained: were entangled particles merely carrying hidden instructions from the start, like the glove boxes, or did quantum theory point to something more non-classical? The answer took a powerful turn with John Bell. In the 1960s, John Bell developed what is now called Bell's theorem. Bell showed that the debate could be turned into an experimental test. If particles carried simple local hidden variables, then the correlations between measurements should obey certain mathematical limits, now called Bell inequalities. Quantum mechanics predicted that entangled particles could violate those limits. In other words, the difference between the classical hidden instruction picture and the quantum picture could be measured in the laboratory. Experiments testing Bell inequalities have repeatedly supported the quantum predictions. Important work by John Clauser, Alain Aspect, Anton Zeilinger, and many others showed that entangled systems violate Bell inequalities in ways that simple local hidden variable theories cannot explain. Modern experiments have closed major loopholes and strengthened the conclusion: nature does not seem to work like a pair of gloves with fixed properties hidden in separate boxes. The correlations are genuinely quantum. This does not mean entanglement allows faster than light messaging. That is one of the most important clarifications. Measuring one particle does not let someone send a usable signal instantly to another location. The individual result of a measurement is still unpredictable. Only when the two sets of results are later compared through ordinary communication do the correlations become visible. Entanglement is non-classical, but it does not break the speed limit set by relativity. The universe remains strange, but not quite reckless enough to hand everyone a cosmic instant messaging service. Entanglement also deepens the measurement problem. If two particles share a joint quantum state, then measuring one part affects how the whole system is described. The question of how possibilities become definite outcomes becomes more subtle. when the possibilities belong not to isolated particles, but to combined systems spread across space. The wave function of the pair may describe a shared state, even when the particles are far apart. Measurement then reveals correlated outcomes that cannot be explained by treating each particle as fully independent. This is why entanglement is not just another strange feature added to quantum physics. It exposes the deep difference between quantum reality and classical intuition. In classical physics, the state of a whole is usually built by adding together the states of its parts. In quantum mechanics, the whole can possess a state that cannot be reduced to separate descriptions of each part. The relationship itself becomes part of the physical description. Entanglement now sits at the heart of quantum information science, quantum computing, quantum cryptography, and precision experiments. But even before those technologies, it forced physicists to face a quiet and difficult truth. The universe is not always made from independent little pieces carrying fully separate properties. Sometimes, at the quantum level, the connection between things is as fundamental as the things themselves. Entanglement shows that quantum systems can become linked in ways that do not fit ordinary classical pictures, but it also leads naturally to a gentler question. If quantum systems can be in superpositions, interfere with themselves, and become entangled across distance, then why does the everyday world look so solid, definite, and calm? Why does a chair not appear in a visible superposition of being here and slightly over there? Why does a cup of tea not spread its quantum possibilities across the table, apart from the usual danger of spilling it? One of the most important answers is decoherence. Decoherence is the process by which quantum systems lose visible interference effects because they interact with their environment. A quantum system can begin in a delicate superposition, with different possible parts of its wave function able to interfere. But as soon as that system interacts with surrounding particles, photons, air molecules, heat, surfaces, or measuring devices, information about the system leaks into the environment. The separate possibilities become entangled with the wider world, and the interference between them becomes practically impossible to observe. This does not mean the quantum rules have stopped working. The deeper theory is still quantum. What changes is that the clean, isolated behavior needed to see interference has been lost into countless environmental connections. A single electron in a carefully controlled experiment may show wave-like interference. A warm dust grain floating in a room, however, is constantly being struck by air molecules and photons of light. Each interaction carries away a little information about the dust grain's position and motion. Very quickly, the delicate quantum relationships that would allow obvious interference become spread through the environment. This helps explain why large everyday objects do not usually appear in visible quantum superpositions. It is not because they are made from non-quantum material. A table, a person, a planet, and a biscuit are all made from atoms, and atoms obey quantum physics. The difference is that large objects contain enormous numbers of particles and interact constantly with their surroundings. Their quantum information becomes entangled with air, light, heat, floors, walls, and everything nearby. The result is a world that behaves, for practical purposes, in a stable, classical-looking way. H. Dieter Zeh was one of the first physicists to clearly develop the idea of decoherence in the 1970s. He recognized that interaction with the environment could explain why quantum superpositions become effectively unobservable at macroscopic scales. Later, Wojciech Zurek became one of the major figures in developing and explaining decoherence theory, especially in relation to how classical reality seems to emerge from quantum foundations. Zurek's work helped clarify how certain stable states survive environmental interaction better than others, making them appear as the reliable states of ordinary experience. A useful example is the double slit experiment. If an electron passes through the apparatus in isolation, its wave function can include both paths, allowing interference. But if the electron interacts with the environment in a way that reveals which path information, the interference disappears. Decoherence explains this loss of interference as the result of entanglement with the environment. The quantum possibilities have not simply been shouted at by a stern measuring device. They have become correlated with surrounding systems, so the clean interference pattern can no longer form. Measuring devices work in this way too. A detector is not a magical object that somehow lives outside physics. It is a physical system made of atoms, electrons, circuits, heat, and materials. When a quantum system interacts with a detector, the result becomes amplified into a stable record. That record is then entangled with the wider environment. The measurement outcome becomes robust, visible, and difficult to reverse. The tiny quantum event leaves a macroscopic trace, like a dot on a screen or a click in a counter. This is also why laboratory isolation is so important. To preserve delicate quantum behavior, scientists often need to shield systems from the environment, cool them to extremely low temperatures, reduce vibrations, remove stray electromagnetic fields, or place them in vacuum chambers. Quantum computers, atomic clocks, interferometers, and precision experiments all depend on controlling decoherence. The less the system interacts with its surroundings, the longer its fragile quantum state can survive. Warm objects decohere very quickly because heat is motion and interaction at the microscopic level. A warm object emits infrared radiation, collides with surrounding particles, and vibrates internally. All of this spreads information into the environment. This is why a cat, a coffee cup, or a sofa does not behave like a clean isolated electron in a double-slit experiment. They are far too connected to the world around them. The universe is constantly, quietly, and very efficiently taking notes. Decoherence does not solve every part of the measurement problem by itself. It explains why interference disappears and why classical-looking behavior emerges so reliably from quantum systems. But it does not completely answer why one specific outcome is experienced rather than another, depending on the interpretation of quantum mechanics being used. That deeper question remains part of quantum foundations. Decoherence is therefore not the full ending to the mystery, but it is a major part of the explanation for why the ordinary world looks definite. The beautiful twist is that entanglement, the same feature that makes quantum physics seem so strange, also helps explain why reality appears stable. When a system becomes entangled with its environment, its delicate possibilities become dispersed into the wider world. The quantum structure remains underneath, but the visible behavior becomes classical. The world does not stop being quantum. It simply becomes too richly connected for its fragile interference to remain visible. So decoherence brings the ordinary world back into view. It explains why atoms can follow quantum laws while tables look solid, why electrons can interfere while dust grains do not, and why reality at human scales feels definite even though its foundations are built from probability and entanglement. The familiar world is not separate from quantum physics. It is what quantum physics looks like after countless interactions have quietly woven it into place. Decoherence helps explain why the ordinary world looks stable, even though its foundations are quantum. But modern physics goes one step deeper than the electrons moving through atoms or photons travelling as packets of light. Today, the most successful description of particles and forces is built around quantum field theory. Quantum field theory combines quantum mechanics with special relativity. Quantum mechanics describes the behaviour of matter and energy at tiny scales. Special relativity, developed by Albert Einstein in 1905, describes how space, time, motion, and the speed of light are connected. When physicists tried to bring these two frameworks together, they found that particles could no longer be treated simply as little objects moving through empty space. A deeper picture was needed. In quantum field theory, the basic ingredients of nature are fields. A field is something that exists across space and time, with a value or condition at every point. The electromagnetic field is one familiar example. In the quantum picture, particles are excitations of underlying fields. An electron is not just a tiny bead travelling through space. It is an excitation of the electron field. A photon is an excitation of the electromagnetic field. In this view, the universe is not mostly empty stage with particles wandering across it. It is filled with fields, and what we call particles are localized disturbances in those fields. This idea may sound abstract, but it helped solve real problems. Paul Dirac made one of the great breakthroughs by developing a relativistic quantum theory of the electron. His work combined quantum mechanics with special relativity and produced a surprising prediction: antimatter. The theory suggested the existence of a particle like the electron, but with positive electric charge. This particle, the positron, was later discovered by Carl Anderson in 1932. It was a striking example of mathematics pointing towards something real before experiment had fully revealed it. The best-known early quantum field theory is quantum electrodynamics. Quantum electrodynamics describes how light and charged particles interact. It is the quantum field theory of photons, electrons, and electromagnetic forces. Richard Feynman, Julian Schwinger, Shinichiro Tominaga, and Freeman Dyson all played major roles in developing it into a precise and powerful theory. Quantum electrodynamics explains processes such as electrons emitting and absorbing photons, light scattering from charged particles, and the subtle magnetic properties of the electron. It is also one of the most accurately tested theories in science. Its predictions match experiments with astonishing precision. This matters because quantum field theory can sound airy and philosophical from a distance, as if physicists have simply decided that the universe is made of invisible mathematical jelly. But the theory earns its place through measurement. It predicts real numbers, real behaviors, and real experimental outcomes. The larger framework built from these ideas is the Standard Model of particle physics. The Standard Model describes the known elementary particles and 3 of the 4 fundamental interactions: electromagnetism, the strong nuclear force, and the weak nuclear force. It includes particles such as quarks, electrons, neutrinos, photons, gluons, and the particles associated with the weak force. It is not a theory of everything. Gravity is not yet fully included in this quantum framework. General relativity remains the best description of gravity at large scales, while quantum field theory describes the other known forces with remarkable success. Bringing quantum physics and gravity together remains one of the major open problems in theoretical physics. A famous part of the Standard Model is the Higgs field. The Higgs field is a quantum field associated with how many fundamental particles acquire mass. The particle linked to this field, the Higgs boson, was discovered at CERN using the Large Hadron Collider and announced in 2012. The Large Hadron Collider accelerates particles to extremely high energies and brings them into collision, allowing physicists to study what emerges. The discovery of the Higgs boson confirmed a central part of the Standard Model after decades of theoretical and experimental work. The Higgs field does not give mass to everything in the same simple way. Much of the mass of protons and neutrons, for example, comes from the energy of the strong force binding quarks and gluons inside them. But the Higgs field helps explain why many elementary particles, such as electrons and quarks, have mass at all. Without it, the structure of matter would be profoundly different. Atoms, chemistry, and the familiar world would not exist in their present form. This modern picture shows how far quantum physics has travelled. It began with blackbody radiation, photons, atoms, spectra, wave functions, and uncertainty. It grew into a framework where particles are not the deepest objects in the story. Fields are. Particles are the excitations that appear when those fields carry energy in particular ways. And yet, the ordinary world remains calm to the senses. A table does not look like a collection of quantum fields. A stone does not announce its quark structure when picked up. The classical-looking world appears because quantum systems interact, decohere, bind into atoms, form molecules, and build stable matter at human scales. Beneath that calm surface, however, the modern picture is field-like, quantum, and restless. So quantum physics is not only the theory of very small particles, It is the beginning of a deeper description of what particles are. The everyday world is built from quantum fields, even when it feels solid, quiet, and reassuringly ordinary. What looks like matter is, at its foundation, the organized behavior of fields obeying quantum rules. Quantum physics can sound as though it belongs only in chalkboards, particle accelerators, and very serious rooms where nobody has slept properly since 1927. But it is not only a theory of tiny things hidden far away from ordinary life, it is also the foundation of much of modern technology. The same ideas that began with photons, energy levels, wave functions, spin and quantum fields now sit quietly inside computers, phones, hospital scanners, lasers, clocks, cameras, satellites, and global communication systems. One of the clearest examples is the semiconductor. Semiconductors are materials whose electrical behavior sits between conductors, which allow current to flow easily, and insulators, which resist current. Silicon is the most famous semiconductor, and it lies at the heart of most modern electronics. But silicon does not work its technological magic because it is feeling helpful. It works because of quantum band structure. In a solid material, atoms are arranged close together, and their electron energy levels combine into bands of allowed energy. Between these bands are gaps where electron states are not allowed. In conductors, electrons can move easily because suitable energy states are available. In insulators, the gap is too large, so electrons do not move freely. Semiconductors sit in between. Their band structure allows their electrical behavior to be controlled by adding tiny amounts of other elements, applying voltages, or shining light on them. This control makes transistors possible. A transistor acts like a tiny electrical switch or amplifier. It can regulate the flow of current, turning signals on and off. Modern computer chips contain enormous numbers of transistors, each relying on quantum behavior in semiconducting materials. Every time a phone wakes up, a laptop opens, a camera processes an image, or a digital clock blinks with suspicious confidence at 3 a.m, quantum physics is working underneath. Lasers are another major example. The word laser refers to light amplification by stimulated emission of radiation. The important idea is stimulated emission, a process Albert Einstein described theoretically in 1917. In stimulated emission, an incoming photon can cause an excited atom or molecule to release another photon with the same frequency, direction, and phase. This produces coherent light, meaning the light waves are highly coordinated. Ordinary light, such as light from a lamp, contains many wavelengths and directions mixed together. Laser light is much more orderly. Its photons can travel together in a narrow, precise beam. That is why lasers are useful in fiber optic communication, barcode scanners, surgery, manufacturing, scientific instruments, and even the small red pointer that somehow makes every cat briefly consider a career in high-speed athletics. Lasers depend on quantum energy levels and photon emission, the same basic ideas that began with atomic spectra. Atomic clocks also rely directly on quantum physics. These clocks measure time using extremely precise transitions between energy states in atoms. A transition is a change from one allowed energy level to another, and the frequency associated with that transition can be extraordinarily stable. Cesium atomic clocks have long been used to define the second, and newer optical atomic clocks use transitions at even higher frequencies to achieve still greater precision. Organizations such as the National Institute of Standards and Technology in the United States, the National Physical Laboratory in the United Kingdom, and other metrology institutes around the world develop and maintain these timekeeping standards. Atomic clocks are not only impressive scientific instruments, they support technologies such as satellite navigation, telecommunications, financial networks, and tests of fundamental physics. Without quantum transitions, modern precision timekeeping would lose its deepest foundation. Magnetic resonance imaging is another technology shaped by quantum behavior. It is based on nuclear spin, magnetic fields, and radio waves. Certain atomic nuclei, especially hydrogen nuclei in the body's water and fat, have quantum spin. When placed in a strong magnetic field, these spins can align in particular ways. Radio waves can then disturb that alignment, and as the nuclei return toward their original state, they produce signals that can be detected and turned into detailed images. This is not medicine by magic. It is physics translated into a medical tool. Magnetic resonance imaging uses quantum properties of nuclei to help reveal structures inside the body without needing ionizing radiation like X-rays. The explanation can become very technical, but the basic principle is beautifully direct. Tiny quantum spins respond to magnetic fields, and those responses can be measured. Electron microscopes also depend on quantum ideas. Because electrons have de Broglie wavelengths, they can be used to probe structures much smaller than visible light can normally resolve. In an electron microscope, beams of electrons reveal fine details of materials, cells, crystals, and surfaces. The wave nature of matter, once a strange proposal from Louis de Broglie, became a practical way of seeing the very small. So quantum physics is not merely a strange theory resting at the edge of understanding, it is part of the machinery of daily life. Semiconductors rely on quantum band structure. Lasers rely on stimulated emission. Atomic clocks rely on precise quantum transitions. Magnetic resonance imaging relies on nuclear spin. Electron microscopes rely on matter waves. The principles that once seemed almost unbelievable now operate quietly in hospitals, laboratories, satellites, factories, homes, and pockets. That may be the calmest surprise in the whole story. Quantum physics did not remain a mystery locked inside the atom. It became useful. The same rules that made electrons look wave-like, atoms emit precise colours, and photons arrive in packets now help power the ordinary world. Beneath the smooth glass of a phone screen, the pulse of a laser, the timing of a satellite, and the image from a medical scanner, the quantum world is not distant at all. It is already here, working quietly, one precise little rule at a time. Quantum technology already shows that quantum physics is not merely a strange description of hidden particles. It can be engineered, it can be controlled, it can be turned into devices that measure, calculate, communicate and process information in ways that classical physics alone would never have suggested. One of the most active areas built from this idea is quantum information. Quantum information is the study of how information can be stored, processed, and transmitted using quantum systems. In ordinary digital technology, information is usually built from bits. A bit can have one of two values, often described as 0 or 1. Every photograph, message, video, calculation, and mildly suspicious online password is ultimately represented through patterns of these classical bits. Classical computing has changed the world by arranging those simple states into astonishingly complex structures. Quantum computing begins with a different unit of information, the qubit. A qubit is a quantum system that can be measured in two basic outcomes, but before measurement it can exist in a superposition of those basis states. Physically, a qubit might be represented by the spin of an electron, the polarization of a photon, the energy levels of an atom, or the quantum state of a superconducting circuit. The crucial idea is that the qubit is governed by quantum rules, not classical ones. This is often described carelessly, as if a quantum computer simply tries every possible answer at once and then magically picks the correct one. That is not how it works. A qubit in superposition does not hand over unlimited free computing power, and a quantum computer is not a cosmic cheat code with a cooling system. If quantum computing were that simple, physicists would look slightly less tired. The real power comes from the careful control of probability amplitudes, interference, and entanglement. Interference is essential because quantum amplitudes can reinforce or cancel one another. A good quantum algorithm is designed so that wrong or unwanted possibilities are suppressed, while useful outcomes become more likely when the system is measured. This is delicate. A quantum computer must guide the evolution of the quantum state so that the final measurement is biased toward the answer being sought. It is not enough to create many possibilities. The hard part is arranging them so that the right structure emerges from the interference. Entanglement is another key resource. When qubits become entangled, the state of the whole system cannot be fully described by treating each qubit independently. This allows quantum computers to represent and manipulate certain patterns of information in ways that classical systems cannot easily imitate. Entanglement does not mean information is being sent faster than light, and it does not mean every quantum computer instantly becomes powerful. It means the information is stored in a joint quantum state, with correlations that have no simple classical equivalent. Richard Feynman was one of the important early voices in this field. In the early 1980s, he argued that because nature itself is quantum, simulating quantum systems might require computers that also use quantum rules. A classical computer can simulate many things, but quantum systems become extremely difficult as the number of particles grows, because the quantum state can become enormously complex. Feynman's insight was calm but profound. Perhaps the best way to simulate quantum physics is with quantum physics. David Deutsch also played a major role in the conceptual development of quantum computing. He described a universal quantum computer, showing that quantum computation could be treated as a general model of information processing, not just a special tool for one experiment. His work helped turn quantum computing from an interesting thought into a theoretical field with clear rules and ambitions. Some quantum algorithms later showed that quantum computers could, in principle, outperform classical computers for certain specialized tasks. Peter Shor developed Shor's algorithm, which can factor large numbers efficiently on an ideal quantum computer. This matters because some widely used encryption methods rely on the difficulty of factoring large numbers with classical computers. Lovegrover developed Grover's algorithm, which provides a speed-up for searching through an unstructured set of possibilities. These algorithms are important not because they prove quantum computers are better at everything, but because they show real theoretical advantages for particular kinds of problems. That distinction matters. Quantum computers are not simply faster laptops. They are not expected to replace ordinary computers for writing emails, watching videos, or opening 37 browser tabs in a quiet act of optimism. Classical computers are extremely powerful and will remain better suited to many everyday tasks. Quantum computers are being developed for specific areas where quantum behavior may offer an advantage, such as simulating molecules and materials, exploring certain optimization problems, and improving some forms of secure communication and sensing. Today, organizations such as IBM Quantum, Google Quantum AI, Microsoft Quantum, and many university research groups are building and testing different kinds of quantum hardware. Some use superconducting qubits, others use trapped ions, photons, neutral atoms, or other systems. The engineering challenges are enormous. Qubits are fragile. Decoherence can destroy the delicate quantum information. Errors must be corrected. Systems must often be cooled, isolated, and controlled with extraordinary precision. Building a useful quantum computer is less like assembling a faster calculator and more like persuading a snowflake to do mathematics while nobody breathes too loudly nearby. Quantum information also includes quantum communication. Quantum key distribution uses quantum principles to help detect eavesdropping, because measurement can disturb quantum states in detectable ways. Quantum teleportation, despite the dramatic name, does not teleport matter or people. It transfers an unknown quantum state from one system to another, using entanglement and classical communication. No one is stepping into a glowing booth and arriving on Mars with slightly rearranged socks. The actual science is subtler, but still remarkable. The larger point is that the same basic principles have returned in a new form. Superposition allows quantum states to hold combinations of possibilities. Measurement turns those possibilities into definite outcomes. Interference shapes probabilities. Entanglement creates non-classical connections between parts of a system. Decoherence explains why preserving those states is difficult. Quantum information takes these ideas and asks how they can be used deliberately. So quantum computing is not a break from the earlier story. It is one of its modern consequences. The ideas that once emerged from blackbody radiation, photons, atoms, wave functions, uncertainty and entanglement, are now being shaped into new tools. They are still difficult, they are still limited, but they show that quantum physics is not only something nature does in secret, it is something human beings are learning very carefully to use. The basics of quantum physics are not a collection of disconnected oddities. They are not merely strange facts about particles behaving badly under laboratory supervision. Taken together, they form a careful, scientific picture of reality at small scales. That picture says the microscopic world is quantized, probabilistic, wave-like, and deeply shaped by measurement. It does not always behave like the smooth, solid, predictable world that human senses evolved to navigate. It follows rules that are precise, reliable, and often profoundly unlike intuition. The older classical picture had been enormously successful. Isaac Newton gave physics a world of motion, forces and gravity, where objects followed definite paths, and future behaviour seemed, at least in principle, calculable from present conditions. James Clerk Maxwell showed that electricity, magnetism and light were joined in one electromagnetic framework. The universe seemed continuous and orderly, a place where energy could vary smoothly, and matter could be pictured as tiny things moving through space with definite properties. Then the cracks appeared. Blackbody radiation refused to match classical predictions, and Max Planck introduced the idea that energy could be emitted or absorbed in discrete packets. Albert Einstein extended that quantum idea to light itself, explaining the photoelectric effect by treating light as photons. Ernest Rutherford revealed the tiny dense nucleus inside the atom, while Niels Bohr used quantist energy levels to explain why hydrogen emitted light at specific colours rather than every possible shade. That was already enough to change physics, but the deeper transformation continued. Louis de Broglie proposed that matter has wave-like properties, and electron diffraction showed that electrons could produce interference patterns. Erwin Schrödinger developed wave mechanics, placing the wave function at the heart of quantum theory. Max Born connected that wave function to probability through the Born rule. Werner Heisenberg introduced the uncertainty principle, showing that certain pairs of properties such as position and momentum cannot both be sharply defined without limit. From there, the theory became stranger and more complete. Superposition showed that quantum states can contain combinations of possible outcomes. Measurement raised the difficult question of how one definite result emerges from a spread of possibilities. Quantum tunneling revealed that particles can sometimes be found beyond barriers that classical physics says they should not cross. Spin and the Pauli exclusion principle helped explain the structure of atoms, the organization of the periodic table, and the very shape and solidity of matter. Then came entanglement, where the state of a combined quantum system cannot always be reduced to separate descriptions of its parts. Albert Einstein, Boris Podolsky, and Nathan Rosen challenged quantum mechanics with the EPR argument, while Niels Bohr defended the completeness of the quantum description in his own careful way. John Bell later showed that this debate could be tested experimentally, and Bell inequality experiments revealed that nature cannot be explained by simple, local, hidden variable theories. Decoherence helped bring the ordinary world back into view. It explained why large objects do not usually appear in obvious superpositions, because their quantum states interact with air, light, heat, measuring devices, and countless surrounding particles. The fragile interference that defines small isolated systems becomes spread into the environment. The world remains quantum underneath, but at human scales it becomes stable, solid, and classical looking. A chair does not stop being made of quantum fields and particles. It simply has far too many environmental conversations to behave like a lonely electron in a double-slit experiment. Modern physics then deepened the picture again through quantum field theory. Particles are not merely tiny beads moving through emptiness. They can be understood as excitations of underlying fields. Paul Dirac's relativistic quantum theory helped predict antimatter, later confirmed through the discovery of the positron by Carl Anderson. Quantum electrodynamics described light and charged particles with astonishing precision. The standard model of particle physics brought together the known elementary particles and 3 of the 4 fundamental interactions, while leaving gravity as one of the great unfinished pieces. And the theory did not remain trapped in abstraction. Quantum physics became technology. Semiconductors rely on quantum band structure. Lasers rely on stimulated emission. Atomic clocks rely on precise transitions between atomic energy states. Magnetic resonance imaging relies on nuclear spin. Electron microscopes use the wave nature of matter. Quantum computing and quantum information now attempt to use superposition, measurement, interference, and entanglement as resources for new kinds of calculation and communication. So what does quantum physics really say about reality? It does not say that reality is fake. It does not say that consciousness magically creates the universe. It does not say that anything can happen if someone simply says the word quantum with enough confidence. Quantum physics is not a permission slip for nonsense wearing a lab coat. It says something more disciplined and more interesting. Nature follows precise mathematical laws, but those laws do not match the old classical picture of definite little objects carrying definite properties at all times. Quantum mechanics is one of the most successful scientific theories ever developed. Its predictions have been confirmed in atomic physics, chemistry, material science, particle physics, precision measurement, and modern technology. It explains why atoms are stable, why elements have spectral fingerprints, why chemical bonds form, why matter has structure, and why devices all around modern life can function. Its strangeness is not a weakness. The strange parts are often exactly where the experimental evidence is strongest. Still, open questions remain. The interpretation of measurement is not fully settled. Physicists still debate what the wave function means, how definite outcomes should be understood, and which interpretation gives the clearest picture of reality. The relationship between quantum mechanics and gravity remains unresolved. General relativity describes space-time and gravitation beautifully at large scales, while quantum theory describes matter and the other forces with extraordinary success. How these frameworks fit together at the deepest level is still one of physics' greatest questions. The nature of quantum fields, space-time, and whatever may lie beneath them remains an area of active thought and research. That is part of the quiet beauty of the subject. Quantum physics is practical enough to build a laser, guide an electron microscope, and support the electronics inside a phone. It is profound enough to challenge old assumptions about what matter, light, probability, and measurement really mean. It does not make the universe less real. It makes reality more subtle. The world still appears steady around us. Tables remain still. Stars shine. Water flows. Clocks tick. Yet beneath all of it, the foundations are not quite the foundations that classical physics imagined. They are discrete, probabilistic, wave-like, entangled, and deeply structured. Quantum physics explains the ordinary world by revealing that, underneath its calm surface, reality is far stranger and far more exact than it first appears. The basics of quantum physics are the principles that explain how energy, light, atoms, particles, probability, measurement, and matter behave beneath ordinary experience. They reveal that the world is not built from smooth certainty all the way down. At the smallest scales, energy can come in discrete packets. Light can behave as photons, matter can show wave-like behavior, and physical outcomes are often described through carefully calculated probabilities rather than simple classical prediction. The story began with the failure of classical physics to explain blackbody radiation and the photoelectric effect. Max Planck's quantum and Albert Einstein's photons showed that energy and light did not always behave as continuous waves. Ernest Rutherford and Niels Bohr revealed that atoms had tiny nuclei and quantist energy levels. Atomic spectra showed that matter speaks in precise lines of light. Louis de Broglie's matter waves, Erwin Schrödinger's wave function, Max Born's probability rule, and Werner Heisenberg's uncertainty principle gave quantum physics its deeper language. From there came superposition, measurement, tunneling, spin, the Pauli exclusion principle, entanglement, decoherence, quantum fields, and quantum technologies. Each idea added another piece to the same calm but surprising picture. Reality is lawful, but not always intuitive. Quantum physics is not a decorative mystery, and it is not a license for magical thinking. It is a precise scientific theory developed because experiments repeatedly demanded a new description of nature. Its predictions help explain atoms, chemistry, materials, lasers, semiconductors, medical scanners, atomic clocks, and the technologies quietly woven through modern life. The ordinary world remains real, stable, and meaningful. Tables are still tables, stars still shine. A cup of tea remains, thankfully, a cup of tea. But beneath that familiar surface, the rules are more subtle than classical physics imagined. Quantum physics does not remove wonder from reality. It deepens it. It shows that the universe is stranger, more structured, and more beautifully understandable than the older clockwork picture could ever fully reveal.